So this is example 3 of Hardy-Weinberg solving. So in a population of flowers, petal color of the flowers is determined by a single gene with two alleles. We have the big P allele, which is dominant and is for the purple petal phenotype. And we have little p, which is recessive and is for the white petal phenotype. In this population, 16% of the flowers have white petals, which is recessive. Assume the population is in Hardy-Weinberg equilibrium. Find the frequency of the big P allele, the little p allele, the frequency of heterozygous individuals in the population, and the frequency of homozygous dominant individuals in the population. So to solve this, we need to use two equations. The first one is P plus Q equals 1, and the second is P squared plus 2PQ plus Q squared equals 1. So P is the frequency of the dominant allele, which is P. Q is the frequency of the recessive allele, which is the little p. Let me give a curse. P squared is the proportion of the population that is homozygous for the dominant allele, which is big P, big P. 2PQ is the proportion of the population that is heterozygous, which is big P, little p. And Q squared is the proportion of the population that is homozygous for the recessive allele, which is little p, little p. So we already know that 16% of the flowers have white petals, which is recessive. So 16%, which is 0.16. So we know that 0.16 equals Q squared, because this is the proportion of the population that is homozygous for the recessive allele, which is little p, little p. So when we take the square root of both sides, we get Q equal to 0.4. And so this is the frequency of the little p allele, which is question 2, 0.4. So to find the frequency of the big P allele, we use this equation, P plus Q equals 1. P plus Q, which is 0.4, equals 1. We subtract 0.4 from both sides, and we get P equal to 0.6. And so this is the frequency of the big P allele, which is the dominant allele. So now we want to find the frequency of heterozygous individuals in the population, and that would be 2PQ, because that is the proportion of the population that is heterozygous, which is big P, little p. So that would be right. So we do 2 times P, which is 0.6, times Q, which is, that is not P, times Q, which is 0.4. And when we type that into the calculator, we get a value of 0.48. So that's number 3. For question 4, we want the frequency of homozygous dominant individuals in the population. So that would be Q squared, because that is the proportion of the population that is home. No, that is not Q squared. I'm sorry, that is P squared, because that is the proportion of the population that is homozygous for the dominant allele. So P squared, we already know P is 0.6, so we just do P squared equals P, which is 0.6 squared. And when we type that into a calculator, we get 0.36. And so that is the frequency of homozygous dominant individuals in the population. And that is Hardy-Weinberg example 3.